How do I pump a coroutine? And what does that even mean? Well, I'm James Powell, and that's exactly what we're going to cover in today's session. Today, we're going to answer three questions. What is a coroutine? Why do we actually pump them? And how would we go about doing that? Unfortunately, one question we will not be able to answer in today's session is, well, where do these actually show up in my work? But if you're interested in getting an answer to that question, please join us on our Discord server where we can have an in-depth discussion about coroutines generators and coroutines and where they may show up exactly in your work. With that said, why don't I share my screen and jump in? We have an enormous amount to cover and we're going to go very quickly. I want to answer for you the very first question. What is a coroutine and what is a collections.abc.Coroutine, and maybe why is it that this terminology seems to be so clumsy? Let's take a look. Well, I'll start you off with something that you already know. This is the thing that we would call a function. It has a def in front of it, it returns something, and it takes some parameters, and we might be able to split those parameters into data parameters and modal parameters. To get a sense of what that means, we might talk about data parameters as parameters that are the thing that we're operating on, and modal parameters as options, flags, modalities that indicate how we do that operation. For a function, we evaluate that function or execute that function by putting open close parentheses after it, and it gives us the result value. It gives us whatever is returned. If we ask Python what it would call this structure, Python internally will call this a function. In fact, you can see that the object here is function. If you dig deeper into the interpreter, you'll see the interpreter makes a distinction between user-defined functions, functions written in Python, as well as C-level functions, functions that may be written in some library and bound up into Python. And so you can see this thing is actually called a function, but in general, for our purposes, what we usually refer to is this as a callable, something that can support the open close parentheses syntax after it, something that can be called. And in fact, there are many things that are callable. You can see this function is callable, but any class that implements the double underscore method, the data model method call, is also a callable. And in fact, the class itself is a callable. That is to say that underscore call is implemented on the meta class itself, and that's what then invokes or creates an instance of this class. If we ask the typing module what this is, it'll tell us that this is a function type, and you can see that for the most part, a callable and a function type line up, except the class itself and the class instance are not considered function types. This function type is actually a way for us to determine, do we have something that is a DEF-defined function or not? Here is something that we'd call a generator. And we can identify this as a generator because it uses that DEF syntax and it has a yield somewhere in it. This generator also takes modal and data parameters, and it seems to have the same general structure as the function in the sense that the data parameters are typically passed as positional arguments, and the modal parameters are typically passed as keyword-only arguments. If we want to work with this structure, what we'll do is we'll invoke it using that call protocol, but that will give us an indirection. It'll give us a generator instance, and on that indirected structure, we'll have to then subsequently use a next in order to actually get a return value. We can think that a generator is a way for us to take effectively what's in a function, a computation that can be broken down into multiple parts, and to structure that computation. And so a computation that is formed out of step 1, 2, and 3 could then be structured as a generator where step 1, 2, and 3 are now delineated. In this regards, when we call the function, we execute all three of those steps without any ability to interleave behavior in between, without any ability to see the partial result of just one of these steps. But when we execute the generator, we can use that next in order to run just step 1, and then step 2, and then step 3, and we can do anything we want in between. Each one of these will give us an intermediate result. It is unlikely that in practice we would see many generators written in this particular way, in part because you can imagine that if we're interleaving a lot of behavior here, as of this line of code, it might be very unclear to us whether or not we're on step 1, 2, or 3. And in fact, this may be just unclear enough that it makes it unusable. In fact, this style of generator is in use in cases where we don't control the execution In other words, where we wouldn't necessarily become confused because somebody else is controlling how these step through, and that is typically some automated event loop. In practice, the kinds of generators we'd see are computations where we don't care exactly where we are in the steps, and the steps themselves are relatively homogeneous in the sense that we probably have some data set that we're iterating over, and each step is just one step through that data step. So this is typically where we'll see generators in play, and what we can think of is this allows us to partially compute the data set, or it even allows us to make this some kind of infinite loop, but not necessarily have an infinite amount of time necessary to actually give us a return value, instead to slice it to control the modalities of how this terminates. If we think about this second way for us to work with the generator, we can see a correspondence in Python. That is to say, the for loop syntax in Python is equivalent to having a while true loop, trying to call next every single time, and if that next call raises a stop iteration, exiting out of this while true loop. And there's a strict correspondence between these two pieces of syntax. Typically, we prefer to write it in this style. Here, if we look at the generator, we can see that the Python interpreter doesn't really refer to generator instances at all. In fact, it's going to be hard for us to find the word generator instance anywhere in the source code for the interpreter. In fact, we'll probably only find this in terms of the documentation. Here, what we call a generator actually turns out to be a function that returns what we call a generator instance. The Python interpreter refers to the instance as the generator, and it returns to this def-define structure as just a regular function. In the types module, we can look at the generator type, and we can see that there's a very close correspondence to what is considered to be a generator and a generator type. Of course, since G is actually a function, we can see that it's a callable, and we can also see that it is indistinguishable from a regular function, what we typically call a function. In fact, behind the scenes at the C interpreter level, there is a hidden flag on the G here that indicates whether or not it's going to run to completion or whether it's going to yield. And that affects how the PyEval frame loop actually builds up the structures necessary in order to do execution. That flag is generally very difficult for us to observe outside of the C level. It's very difficult for us in pure Python to determine whether something is going to give us a generator back, give us a generator instance back, or just be a function that runs to completion. The reason for that we can think about is because this particular syntax here, what we'd call comprehension syntax, building a generator expression, directly creates just one of those things that we'd call a generator instance, or what the Python interpreter calls a generator. And because we could have something with a yield in it, or we could have something with a return in it that returns this generator instance, or we could have a lambda that returns this generator instance, this generator expression, it would be very difficult for the Python interpreter to meaningfully distinguish these three structures. And because these two structures here could have some sort of arbitrarily complex behavior that leads to this result, well, it could turn out to be the case that without some very good static analysis, it would be very difficult for us to really tell, is this a function or is this a generator function? Interestingly enough, it is the presence of the yield that determines whether or not this thing is a generator or not, even if that yield is unreachable. In this particular case, we do get a generator, even though there is no way for us to reach this yield statement. And in fact, in cases where the yield may not even appear in the bytecode, for example, if it has been elided from the bytecode as a consequence of being under a branch that is unreachable, as a consequence of, for example, using the debug flag and running with -o optimizations, this thing is still a generator. And so the mechanisms behind the scenes that make this a generator actually occur before the Python interpreter will do this pruning of unreachable code. It is really the presence of a yield somewhere in this function, even if it's not reachable, even if it's not present in the resulting bytecode, that turns this into a generator. Here is something that we call a coroutine. The reason we call this a coroutine is because from a computer science perspective, we would refer to this as a generalization of a subroutine. We might call a function a subroutine if we're over a certain age, but we definitely call this a coroutine if we're thinking in terms of, well, is this some entity that performs a computation that has been broken down into parts where we can not only get partial outputs, but also send in partial inputs? The distinction between a generator and a coroutine is very slight. From the Python interpreter's perspective, they're the same thing. But from our perspective, we would say that a coroutine is any case where we have something defined with def, has a yield, and we actually look at the result of that yield expression. There's an equal sign here. If we want to work with this coroutine, we'll first instantiate it to create what we'll call a coroutine instance, and then we'll use the .send method in order to send additional data in, or use the next method in order to send a none value in. In either case, we'll send some partial input in, and we'll get some partial output back out. If we ask the Python interpreter what this thing actually is, it will tell us that this thing is not a coroutine. What the Python interpreter calls a coroutine has no relationship between what we here are calling a coroutine. Because our use of the word coroutine here is to refer to a computer science concept, not necessarily a concept that is present in all versions of Python. In fact, what the Python interpreter calls a coroutine did not exist prior to Python 3.6. Here we can see that neither of these are coroutines, but they are in fact generators, and the Python interpreter really doesn't distinguish between the idea of a generator and the idea of a coroutine as we have described it. This is because in Python 3.6, new syntax was added, the async await syntax, and things that are defined with async def are what the Python interpreter refers to as coroutines. The reason that it uses this terminology is prior to the introduction of this syntax, we would implement the same behavior by using generators and some additional mechanism around them. And so anything defined with an async def is what we might call an asynchronous task, but what the Python interpreter will call a coroutine. In order to evaluate this coroutine, we need to launch it into something that is aware of the event loop. So we'll use something like async.io run in order to launch this directly into an event loop, which can schedule its operation, or we'll call it from within something that is already within the event loop using this await syntax. In either case, the only way for this asynchronous function to run is in the presence of an event loop and aware of an event loop. What that means is we cannot evaluate this asynchronous function from a synchronous function here, because this synchronous function here is not aware of there being a scheduler, of there being an event loop. And so this is invalid. If we ask the Python interpreter what this thing is, it will tell us, finally, this thing here is a coroutine. This, however, is not what the Python interpreter calls a coroutine. This is also a function. In fact, from the Python interpreter's perspective, what we called a coroutine, what we called a generator, what we called a function, and what we're calling an asynchronous task are all just functions. It's just what they return that happens to either be a generator or a coroutine. If we put a yield inside of this structure and we have both an async def and a yield, we get what we might call an asynchronous generator. Here we have the combination of both of these ideas. Like the regular generator, this takes some data and some modalities, and if we want to actually evaluate this, we'll have to evaluate it from within something that's aware of the event loop. In other words, by using async.io.run on it, or by using the await syntax together with something that has already been launched into something that's aware of the event loop. Here you can see that we can evaluate this asynchronous generator in roughly two ways corresponding to the two ways that we evaluate a generator. We can either call a next on this, or we can do an async for loop. And you can think just as we have a correspondence between a for loop and the use of the next operator as well as the iter operator, in the asynchronous world, we have a correspondence between the a next syntax as well as in the async for syntax with the a iter and a next. So we have these two correspondences available to us, both the synchronous and the asynchronous side of it. If we were to make use of the return value of this yield expression, this is what we might call an asynchronous coroutine. It's an asynchronous generator that's also receiving data back in, but the terminology starts getting very messy. Here, if we want to evaluate this thing, we'll have to use an asend operation instead of a send operation. And if we ask the Python interpreter what this is, the Python interpreter say this is an async generator. It won't actually distinguish this thing from this thing here. And so, in summary, we have some very confusing terminology in front of us. This is what we might call a function, or if we're over a certain age, we might call this a subroutine. This is what we might call a generator, or if we want to be really strict, we'll call it a generator returning function. By the way, nobody calls this thing a generator returning function, even though it's the most appropriate way to describe this, taking account of how the Python interpreter looks at this. This thing we might call a coroutine with the lowercase c to imply that we're using the computer science definition of a coroutine, that is a generalization of a subroutine, or to be specific, we could call this a generator coroutine, or we could call this a generator with send, or we could call this a generator coroutine returning function. But all of those are terrible names, so I don't think lowercase c coroutine is really that bad of a name. This thing here, we could call it collections.abc.Coroutine, because that's what the Python interpreter will say. Definitely that's what this is. Or we could call it an awaitable or asynchronous function task or coroutine. We could call it a coroutine returning function. But these are also terrible names, except for maybe asynchronous function or asynchronous task. And so I think calling this an uppercase C coroutine is not that bad. I guess it's only marginally worse than calling it an asynchronous function or asynchronous task. This would then be an asynchronous generator, or more strictly, an asynchronous generator returning function. Again, the nomenclature here is not very, very easy for us to adopt or easy for us to parse. And thus, this last result is what we might call an asynchronous generator with send, terrible name, an asynchronous or awaitable coroutine squared, even worse, or, and I don't think it's that bad, this could be a lowercase c, uppercase c, coroutine, because it's both a coroutine from the computer science perspective and a coroutine from the Python interpreter perspective of being something that can be scheduled. Now that we know what we're referring to when we talk about coroutines, let's talk about why we'd ever want to pump one of these things. Let's take a look. It turns out when we're working with generators, there is an implicit modality in play. That is to say, when we work with a generator, or when we work with a generator coroutine or a coroutine here, and we send something into it, if we try and send a value in immediately after creating the instance, we'll get this error. Can't send a non value to a just started generator. And what we can see here is there's a modality. The first time we do something, it's slightly different, and every other subsequent time we do something, it's the same. In other words, we have to put a next here or a ci.sendNone at the very beginning, but ever after, we can do whatever we want. There's something special happening in that first step. If we were to disassemble this thing and look at what's happening behind the scenes, we can see a little bit about why this is the case. We can see from the bytecode that the coroutine here first yields a value and then stores what you are sent in. And so strictly, the code here is running linearly. Something has to come first. You either transmit first or you receive first. If we try the same thing with an asynchronous generator or an asynchronous coroutine or an uppercase C coroutine, whatever you want to call it, we'll see that we have exactly the same case. The error message is almost identical. Here it says we can't send a non-none value to a just started async generator. But in any case, there's an implicit modality. There's something special that we have to do if we are doing this the very first time. Here, we can see a common example of something that we might just call a generator. This is the equivalent of itertools.repeat. Here, we have something that just loops over a value infinitely. If it were the case that we wanted to change the value that we're looping over, then we'd want to send something back into this structure. Here we have an extension of the idea of an itertools.repeat. We have this thing called latch, where we loop over a value until you decide to latch in a new value. Remember that next call is the same thing as sending in none. That's why we have this guard clause right here. Well, we can think that there are two choices for how we could structure this. We could transmit a value before we receive the value, or we could receive a value before we transmit a value. And the difference here would show up as following in the output. If we transmitted before we received, we would be able to operate on the value that we sent in, and in the same line of code, give back something that is computed based off of that. If we received before we transmitted, we'd send something in and we wouldn't see the result until one more call later. The Python interpreter chooses to transmit before they receive, and therefore we have the behavior that you can see here. And this is why we can't send a non-none value, because we can't receive a value in this structure before we've transmitted something, and so a non-none value would just get lost. It wouldn't be able to be received anywhere. We must yield before we can get the return value of that yield expression. Now you might wonder why it is that we'd want to rewrite this loop as a latch. Why would we want to update the values that we're looping over? And it seems to be the case that if we didn't have control over all the instances, all the references to this looper, for example, if we had this looper and we passed it into some other structure, like here a data class, and this data class operated on it, well, if we wanted to change the value of this state, the thing that we're looping over, we'd have to reach deep into this structure in order to change this. And we're not guaranteed to be able to do this in any clean fashion. We're not guaranteed to be able to find every instance of this entity. As a consequence, we might actually want to update this running computation in place. You can think of this as equivalent to the idea of when we do a clear operation or a del with a full slice on a list versus just assigning the list to a new value. If there were another reference to this value, well, in this case, both x's and y's will show as empty, but in this case, only x's will show as empty. In some cases, we may want the thing that we're looping over to update in place and all references to update in place. And so this behavior is something that is desirable. It is also the case that we may genuinely want to observe the modality of being first. In fact, you have seen us write ny's longest, first and last, for the specific reason of wanting to observe the modality of when we're looping, are we at the very first thing that we're seeing, or are we at the end looking at the last thing? And here you can see we're able to identify with this iteration helper the first three elements and the last three elements of something that we're looping over. And so the presence of this implicit modality isn't necessarily something that's bad or something that we want to avoid. It's merely the case that we may not be able to effectively observe the modality in some cases, even though we know in other cases we definitely affirmatively want to observe the modality. In compositional situations, however, it may not be possible for us to observe this modality. Let me show you an example. Here, I'm taking two coroutines and I'm chaining them together. And in the execution code here, I may not be able to observe whether I'm at the very beginning of one of these two coroutines. I may not know. Am I at the beginning of the first one that I chained? Am I at the beginning of the second one that I chained? Am I at the beginning of the third one that I chained? In this compositional circumstance, I may not be able to observe if I'm first or not. And as a consequence, I may not know if I'm allowed to send in a non-none value. Here, in this case, we can see, well, itertools.chain doesn't even implement any of the send or throw protocol. It doesn't even implement any of this at all. And so if we want to observe the problem here, well, we'll have to re-implement chain. Here, we've re-implemented chain by just going through each coroutine that we've sent in and yielding from that coroutine using PEP 380 delegation to a subgenerator. But note, in this case, we're actually able to send in a non-none value. You may not know this about yield from, but if you look at the bytecode for yield from, you will see that yield from implicitly does a send of none before it goes through the rest of, before it delegates to that subgenerator. In fact, this is what we will call pumping, and you will see that yield from implicitly already does pumping for you. This is something that can be very confusing if you're not aware of it, and if you're trying to do complex compositions of coroutines. Here I have another implementation of chain that will actually preserve the sending behavior and will not include that implicit pumping. And so here you can see I'm not using yield from, I'm just using .send with some loop catching a stop iteration. And I'm using the same correspondence between the for loop and the while loop that we discussed previously. Now I can chain two of these coroutines, and I can see that at this step here, I can't send a non-none value in without getting an error. If I send a none value in, everything is fine. Now I've illustrated the problem. You can see why this is a problem. How do I know that I need to send a none value here and not send something else in here, especially if these things could be programmatic in some fashion? I wouldn't necessarily know if I'm in that first modality or not. The idea of pumping or priming is the idea of eliminating the first modality, trading it for a last modality, which may or may not exist. Here is our common decorator for doing a pumping or priming operation. What we'll do is we'll instantiate the coroutine or generator, and we'll just call next on it once to move us past the very first yield. We'll add a dummy yield at the very beginning. This is not a dummy value that we're accepting here. This is the first input value that we're accepting here. And we may or may not add a yield at the end that is not able to accept a value because we won't be able to do anything with this value. In the absence of a final yield here, we can't actually operate on that last value. So this would also maybe be considered a dummy yield to encode that last modality. But note, the last modality is not guaranteed to exist because this thing could be infinite, in which case there may not be any last step. It's a very interesting idea. There's always guaranteed to be a first modality. There's always guaranteed to be a first step, but there is not necessarily a last step or a last modality in the case of something that is infinite. This justifies why we would do this pumping or priming. Maybe we can make a better accommodation for the presence or non-presence of a last modality because we may have only infinite coroutines, in which case we're not really losing anything because we'll never hit that last modality. And so here, we've eliminated all modalities from this structure. Here I have an implementation of chaining and an implementation of the coroutine that uses this pump decorator to artificially call next the moment this thing is constructed. And we can see that I have no modalities at all. I can always send a non-end value into the structure no matter what. This is what we call pumping or priming, and this is exactly why we want to do this. In order for us to compose coroutines into larger structures, we will have to deal with this modality one way or another. Otherwise, we end up with code that is very difficult for us to reason about. Here, you can see our latched used together with this chain and with one more reimplementation, a very simple reimplementation of itertools.islice, and you can see that we've connected two latches together, and at any point in time, we can send in a new value to be latched over, and everything works exactly as we would expect. I'd like to answer for you the question now of how do we pump a lowercase c, uppercase c coroutine. Let's take a look. Here is our decorator for pumping a regular coroutine. What we do in this decorator is we instantiate the coroutine, and then we call next on the coroutine to get us past the very first yield. Thus, we are able to send a non-end value to the structure, and we just return the coroutine that we've instantiated. In the structure here, we'll get at least one dummy yield at the beginning, and we may get a dummy yield at the end depending on whether or not we care about that last modality. This allows us to always send in a value from the very beginning. One additional thing we might do is what we might call unification. In addition to pumping this thing, sending in that first value, we may also wrap the coroutine instance in a lambda and return that lambda instead. So what we get from this is not something that we can call send on, but something that is indistinguishable from a function. Here we're unifying the API of a stateless function, and here what we could think of as a structured stateful function. And we could think of this largely as the equivalent between having a template string either be the string itself that you call methods on, or the function.format, which then unifies this with the idea of any arbitrary function so that later on we can swap this out with whatever we want to swap this out with any arbitrary complexity. So we allow ourselves to escalate the complexity of this code more readily. If we try the same thing with an asynchronous coroutine, with a coroutine, what we'll see is, well, we can't use next on a coroutine. It doesn't implement that _next method. We have to use anext. But we can't use anext because anext has to be awaited. It has to be aware of an event loop. And we can't use await anext because the decorator here operates in the non-asynchronous domain. It operates in the synchronous domain. It has no awareness of the event loop. So none of these approaches work. What was elegant about the original approach is we returned the original coroutine back without wrapping it in any fashion. So our runtime overhead is quite minimal. But none of these three approaches will work for a coroutine. Remember, when we're applying a decorator, the decorator is applied when the function is created, and the decorator is applied synchronously. Now, it is possible, because this decorator syntax is the equivalent of just writing this, that we could write an asynchronous decorator as long as all of this were in some asynchronous context. But remember, the event loop that exists when the function is being decorated is not guaranteed to be the event loop that exists when the function is being executed. And as a consequence, there is necessarily a gap in time between the creation of the function and the execution of the function. And that gap of time is almost certainly going to make it impossible for you to have the exact same event loop in both places. And so this decorator approach is going to be problematic. What we could do is we could defer the presence of the event loop by decorating this with something that creates an asynchronous function. But unfortunately, what this does is it changes our syntax for evaluating this thing. Now that we've returned an asynchronous function from this structure, we have to put an await here after we've executed it, which we didn't have to do with the non-pumped version. With the non-pumped version, we can do the following. Here, let's do a none value. But with the pumped version, we have to await this, which means we can now observe a distinction between a pumped and a non-pumped coroutine, or a pumped and a non-pumped coroutine squared, I should say. And that is not really desirable because we wouldn't want to be aware of that dichotomy, especially in a unification circumstance. And so this is a very undesirable way for us to do this pumping operation. Unfortunately, the only other way that we can do this is by wrapping the entire coroutine structure and re-implementing anext, asend, and athrow, and in anext or asend, doing the pumping operation here. Here you can see I'm pumping it just once in asend. This may not be strictly correct. We may have to deal with it here as well. But we have to wrap this entire structure, giving us additional runtime overhead in order to preserve the calling syntax and to make this indistinguishable from a non-pumped coroutine or asynchronous coroutine. So you can see the answer to how do we pump an asynchronous coroutine. Well, the answer is we don't really have a very good answer for this. And both cases are undesirable. Either we change the calling syntax or we add an extra wrapping layer. Unfortunately, the answer is we have only these two choices. But if you're interested in this topic and you want to see where we can use coroutines better in our work to empower much more flexible frameworks, and you want to see how we might be able to rewrite the entire itertools module to support pumped coroutines and pumped coroutine squares, well, I invite you to join us for one of our upcoming sessions. Join us on Discord. We'll be publishing all of those sessions soon. But until then, I'll see you next time.